Now we're at the point of this course where we can use information about the function's derivative, and its second derivative to sketch a very accurate graph of a function. So the procedure that we're going to follow in order to do this is essentially a way to keep track of some of the useful information that we're going to need in order to get an accurate graph. So first we'll start with the information about the function. First and foremost, we would like to know the domain of the function. Where is it defined? And then it's just a natural stretch to talk about where it's continuous. We want to be able to identify all the bad spots if there are any. Intercepts are useful, both x-intercepts and y-intercepts, so those can be found from techniques from pre-calc. Symmetry is also useful. And what that means is if a function is even symmetric, we would like to be able to take advantage of that. So even symmetry is kind of like pages in a book. You have this left-right symmetry, and that occurs when f of x is equal to f of negative x. And then you've also got another symmetry called odd symmetry, where essentially you've got two flips. So negative f of x equals f of negative x. We also want to talk about asymptotes. So horizontal and vertical asymptotes. Horizontal asymptotes, if we need, we could use limit laws or L'Hopital's rule. Vertical asymptotes, those get discussed very closely when you talk about continuity. So again, these are to do with limits. These four items are all information about the function. With the exception of perhaps using L'Hopital's rule, there's no need for a derivative. At this stage, we want to transition to the derivative. We would like to figure out where the function is increasing or decreasing. And then we would like to talk about any minima and maxima. Now, in both of these situations, the first derivative test will be indispensable. So these two items are information about f prime. And finally, we would like to talk about concavity. So where is the function concave up and concave down? And then we'll talk finally about inflection points. And these two items then become information about f double prime. So you can see that this is a nice topic here. Graphing functions using calculus is nice because in some way it's a summary of everything that we've done in this course. We bring together all of these big concepts to be able to talk about how to sketch the graph of a function. The function that we'll talk about is as follows. We're going to take a look at a function that has both a root and a polynomial. So we'll talk about the function negative x to the power of 2/3 times x plus 5/2. So we'll go over our procedure here. We're going to talk first about information regarding the function. And let's talk about a domain and the continuity. F is a product of a root and a polynomial. This root is a cube root that eventually gets squared. So there are no issues with it being undefined anywhere. This root is continuous everywhere. This polynomial is also continuous everywhere. And so putting them both together by using the ideas we've talked about in chapter 2.5, our function is continuous everywhere. So that means there are no holes, no gaps, no jumps, no breaks. This is a very nice function in that regard. It will have other interesting features later. The next thing we want to talk about are the intercepts. Let's talk about where this thing crosses the x-axis and y-axis. So the x-intercepts happen when you solve f of x equals 0. Now, luckily for us, this function is already factored. Remember, one of the themes of this course is that factoring functions makes your life easy when it comes time to figuring out important information. We are going to see that with the derivative and the second derivative. It's very straightforward to see that one of the axis intercepts will be at 0, the other one will be at negative 5 over 2. So the x-intercepts of this function, there's 1 at the origin, and then there is 1 at the point negative 5/2 and 0. Now, because of this, you could then very easily see that if you want the y-intercept, because this is a function, it can only have one output, and that means it has to be at the origin. If you wanted, you could just plug in 0 and get the result the same way. So we now know something about where this function crosses the axis. We'll talk a little bit about symmetry. Now, the function that we've got here, you could think of as being written in function notation. And when it's written in function notation this way, it makes it a little bit easier to understand what to do or what to look for. Whatever goes in this entry has to be copied and pasted there. So it makes sense, just from an efficiency point of view, to talk about even symmetry first. And that means let's plug in negative x wherever we see a placeholder x and see what the function gives us. There's a square power in this root, so it's going to effectively get rid of that negative sign. The one from out front will stay around though. So we'll have negative x to the 2/3, negative x plus 5 over 2. Now, this is not equal to the original function, so there is no even symmetry. There's no left-right symmetry. There's no mirror image on either side of the y-axis. The reason I suggest that you do even symmetry first is that you can then study whether or not the function has odd symmetry. And that means all you need to check is putting another negative sign in front of the answer that you just got from above. When you put another negative sign in front of the answer you just got above, if you get the original function you started with, then it does have odd symmetry. So these two negatives in the front will multiply to give you a positive one, but what we have at the end of the day, unfortunately, is not equal to the original function. There's another negative inside there that just doesn't exist in the original. So this function has no symmetry that we can identify nicely here. Moving on, we'll talk about asymptotes. Now, the function is continuous from negative infinity to positive infinity. That means it cannot have any vertical asymptotes. That's why that initial stage is very important. Horizontal asymptotes happen when you talk about the limit of your function when you go really far out to either the left or the right. Now, the way that this function is written, this is going to turn out that we'll need to talk a little bit about some analysis. And what I mean by that is no limit laws will apply. If I were to sneak a peek here, I would just see a very large number. And that means no limit laws. And if I talk about an analysis, when x becomes a really large positive number, x to the 2/3 still ends up being a really large positive number. Because when you take either a square or a cube root or both, they both get really big. X plus 5/2 also just gets really big. Their product becomes really big times really big, which is really big. But the key difference here is that we've got a negative sign in the front. So yes, the product of the two factors becomes large and positive, but at the end of the day here, we become large and negative. So there is no horizontal asymptote as x goes out to infinity. Now on the other side, we're going to do a similar sort of thing. If we were to take the limit, sneak a peek, and see what we get, you're going to get the same sort of discussion happening. We've got this product. It becomes large. And so once again, no limit laws. We'll talk about analysis. So as x becomes really large and negative, x to the 2/3 regardless becomes large and positive, because that 2 there is a square. So regardless of whether you do the root first or the square first, at the end of the day, this quantity becomes large and positive. This quantity becomes large and negative because there's nothing preventing the sign of x from changing over on the other side. Their product becomes large and negative. Something really big and positive times something really big and negative is really big and negative. And finally, if I were to put in a negative sign in the front, that goes to positive infinity. Once again, there's no horizontal asymptote as x goes to negative infinity. The function just wants to go down, whereas in the other case, the function just rises. So these first 4 steps are really about gathering information to do with the function itself. In the next video, we'll talk about how to gather information for the first derivatives and second derivatives, and then we'll put it all together and sketch